Hello. Today we're going to talk about series of functions. Let's review some ideas from before when we discussed sequences of functions. Let I be a closed interval from a to b, and consider a sequence of functions f sub n defined on I. We'll say that the sequence converges pointwise to a function f, also defined on I, if, once we fix p, given a positive epsilon, there exists a delta such that in absolute value, f sub n of p minus f of p is less than epsilon whenever n is greater than delta. Similarly, we'll say that the sequence is uniformly convergent to a function f if, given a positive epsilon, there exists a delta such that in absolute value, f sub n of p minus f of p is less than epsilon whenever both n is greater than delta and p is in our closed interval. Observe that pointwise convergence means that delta might depend on p, whereas uniform convergence means that delta does not depend on p. In either case, we'll say that f is the limit as n increases without bound of f of n, or that the functions f sub n tend to f. We have the following criteria for determining when a sequence is a uniformly convergent sequence. Again, let I be a closed interval from a to b and consider a sequence of functions f sub n defined on I. The sequence is uniformly convergent if and only if, given a positive epsilon, we can find the delta such that in absolute value f sub m of p minus f sub n of p is less than epsilon whenever both m and n are greater than delta and p is in the closed interval I. We have a series of three results which explains the importance of having a uniformly convergent sequence. Again, let I be a closed interval and assume that the f sub n's is a uniformly convergent sequence of continuous functions on I. Then the limit f is also a continuous function. Similarly, let I be an open interval and say that the f sub n's define a uniformly convergent sequence of uniformly continuous functions f sub n. Then not only is the limit f a uniformly continuous function as well, but we can interchange limits in the following sense. For every point p, the limit as n increases without bound of the limit as x tends to p of f sub n of x equals the limit as x tends to p of the limit as n increases without bound of f sub n of x. Finally, we have a statement about derivatives. Say that I is a closed interval and the f sub n's define a pointwise convergent sequence of differentiable functions f sub n such that the f sub n primes forms a uniformly convergent sequence. Then the limit f is a differentiable function and its derivative f prime is the limit over the f sub n primes. Let's use all of this now to define a series of functions. We've seen some criterion for when a sequence of functions f sub n that are continuous has a limit f that is also continuous, and we have a criteria for when this limit is a differentiable function. However, let's return back to Weierstrass's original example. We found before that the limit s of x is really the limit of a sequence of functions f sub n, where s sub n is actually involving a sum of functions, not just the sequences s sub n. We'll use this to motivate some definitions today. Let I be a closed interval from a to b and say that the f sub n's define a sequence of functions on I. We'll construct a new sequence of functions s sub n as the partial sums of these functions. That is, s sub n is the sum f1 plus f2 plus f sub n. We'll say that this sequence of s sub n's is a uniformly convergent sequence to a series S if, given a positive epsilon, there exists a delta such that in absolute value s sub n of p minus s of p is less than epsilon whenever both n is greater than delta and p is in our closed interval I. In this case, we will write s of x as the infinite sum, or if you will, as the series, f1 of x plus f2 of x plus so on and so forth. We have the following test, which allows us to determine when such a sequence is a uniformly convergent sequence. Let I be a closed interval, and let's consider a sequence S sub n defined by partial sums f1 plus f2 plus f sub n. Let's assume two things. First, there exists real numbers m sub n such that in absolute value f sub n of x is less than m sub n for all x in our closed interval I. And second, the infinite sum over the m sub n's converges. Then the sequence of the S sub n's is a uniformly convergent sequence. Let's explain why. First, let's define a sequence of real numbers a sub n, where the a sub n's are the partial sums m sub 1 plus m sub 2 plus m sub n. By assumption, this is a convergent sequence, therefore it is a Cauchy sequence. This means, given a positive epsilon, we can find a delta such that in absolute value a sub m minus a sub n is less than epsilon whenever m and n are greater than delta. Now, we'd like to show that the same is true for the difference Sm of p minus Sn of p. But this is simply a repeated exercise in the triangle inequality. That is, the absolute value of Sn of p minus Sn of p is less than or equal to the absolute value of a sub m minus a sub n for any point p in our closed interval I. But we just said that this difference is less than epsilon, so we do indeed find that our sequence of S sub n's is a uniformly convergent sequence of functions. Now we'd like to present two results that explain when our series is either a continuous function or a differentiable function. As before, let I be the closed interval from a to b, and consider a sequence S sub n's defined by the partial sums f1 plus f2 plus f sub n. First, we have the term-by-term continuity theorem. Let's assume that each f sub n is a continuous function in our closed interval, and that our sequence S sub n converges uniformly to some function s. Then our series S is a continuous function. Next, let's focus on the term-by-term differentiability theorem. Let's assume three things. First, that each function f sub n is a differentiable function on our closed interval I. Second, that the derivatives s sub n prime converges uniformly to some function g. And third, that the sequence s sub n evaluated at p is a sequence of real numbers that converges for some point p in our closed interval. Then, the sequence S sub n's of functions converges uniformly to a differentiable function s, whose derivative s prime is equal to g. The first statement here follows directly from the continuous limit theorem, so let's focus solely on the second statement. Assuming that each f sub n is a differentiable function, we see that the derivatives of the partial sums, namely Sn prime, is also a differentiable function. So we will show then that the S sub n's converges uniformly as a sequence of functions. Then, as a special case, we'll say that the sequence converges pointwise, so we'll be able to use the differentiable limit theorem to imply that the derivative S prime is just the limit over the Sn primes. To this end, say that a positive epsilon is given. Using the Cauchy criterion for uniform convergence, we must exhibit a delta such that in absolute value, S sub m of x minus S sub n of x is less than epsilon whenever both m and n are greater than delta and x is in our closed interval I. Let's observe a couple of facts. First, since each partial sum S sub n is differentiable and the sequence S sub n prime converges uniformly, we'll use the mean value theorem for the difference Sm minus Sn, as well as the Cauchy criteria for uniform convergence, to find a capital N sub 1, such that whenever m and n are greater than delta 1, and x is different from p, we then have this difference, Sm of x minus Sn of x minus Sm of p minus Sn of p, all divided by x minus p, must be less than epsilon over twice absolute value b minus a. What's happening here is inside of the absolute value, we can rearrange the terms to see that we have Sm of x minus Sm of p divided by x minus p. This will be equal to Sm prime of q for some q between x and p. Similarly, we'll have Sn of x minus Sn of p divided by x minus p. This will be equal to Sn prime of q for some q between x and p. But now, since Sn prime is a uniformly convergent sequence, we see that this difference here, we can make as small as we want. And the point is that everything we see is independent of the choice of p. Now, the sequence Sn of p must converge for some fixed p, so we see that it must be a Cauchy sequence. This means that we can find some delta sub 2 such that Sm of p minus Sn of p is less than epsilon over 2 whenever m and n are greater than delta 2. Putting both of these together, let's let delta be the max of these delta 1 and delta 2. Then for all m and n greater than delta and any x in I, we see that the absolute value of Sm of x minus Sn of x must be less than epsilon over twice absolute value b minus a times absolute value x minus p plus epsilon over 2. Now, here's where we are crucially using the fact that we have a closed interval I between a to b. This means that the absolute value of x minus p is at most the absolute value of b minus a. So putting all of this together, we do see that the absolute value of Sm minus Sn of x must be less than epsilon. Let's now put all of this together and revisit Weierstrass's function from before. We'd like to prove two statements. Assume that a and b are real numbers such that 0 is less than a is less than 1. First, our sum S of x, which is the exact same series that Weierstrass defined, is both well-defined and continuous. Second, if S is not a differentiable function, then we must have a times b is greater than or equal to 1. This at least gives us a necessary condition for when this function S cannot be differentiable. As a remark, the English mathematician Gottfried Hardy showed in 1916 that S is not differentiable when 0 is less than a and a times b is greater than or equal to 1. This means that these conditions actually give us a necessary and sufficient condition for when the Weierstrass function is not differentiable. Let's show the first statement. We'll consider the partial sums S sub n in terms of f sub n, which is a to the n times cosine of b to the n times pi times x. We see that the absolute value of each f sub n of x is bounded by the numbers m sub n, which are equal to a to the n. And in fact, if we consider the partial sums of these m sub n's, we see that actually the sum must converge, and therefore we can use the Weierstrass M test to see that our sequence S sub n must be a uniformly convergent sequence of functions. Indeed, this means that our limit, our series S of x, is indeed a well-defined function. Moreover, each f sub n is a continuous function, so the term-by-term continuity theorem asserts that the series S must also be a continuous function. Finally, let's show the second statement. Let's assume, moreover, that a times b is between 0 and 1. We'll show that our S is differentiable. This means that by considering the contrapositive, if S is not differentiable, then a times b must be greater than or equal to 1. Indeed, let's consider fn prime of x. The absolute value of fn prime of x is less than or equal to a times b to the n. So by using the Weierstrass M test again, we see that our derivatives Sn prime must form a uniformly convergent sequence of functions. Now, by the term-by-term differentiability theorem, we see that our series S must be a differentiable function. Thanks very much for watching.